Everyone, my name is Yiwen Ho, and I'm excited to be here to share our recent work improving offline reinforcement learning with inaccurate simulators. This is the outline. Offline reinforcement learning learns the policy from fixed dataset without risky and costly interaction with the environment, showing great potential in many robotic tasks. The key challenge in offline RL is the OOD issue due to the limited dataset. Most current works deal with it by conservative OOD estimation. However, being too conservative leads to suboptimality. Are there other ways to address OOD issues? In many robotic applications, an inaccurate simulator is often available, so we can utilize the simulator to supplement the limited offline dataset. However, there are two main challenges. Firstly, the exploration-exploitation dilemma when collecting data in the simulator. Excessive exploitation will lead to a suboptimal policy, while rollout from the initial state distribution will lead to low quality or aimless exploration. So our goal is to balance the exploration in the simulator and the exploitation of the offline dataset. The second challenge is the dynamics gap between the real world and the simulator. Due to the dynamics gap, for the same state action pair, S in prime is not equal to S real prime. This discrepancy leads to different target Q values and results in estimation errors for QSA. Therefore, our goal is to reduce the side effect of inaccurate simulator for more accurate Q value estimation. Previous work H2O also combines the offline dataset and the simulator. However, it demonstrates poor exploration when collecting data and is too conservative when training policy. To address these issues, we first pre-train a GAN model with the offline dataset to fit the offline state distribution. After that, we iteratively collect data using the inaccurate simulator and train the policy with the mixed dataset. In the pre-training module, the generator is trained to generate states that align with the state distribution of the offline dataset, and the discriminator is trained to discriminate whether a given state is in distribution or out of distribution. During data collection, we interact with the simulator from the restart distribution provided by the generator to avoid aimless exploration. For the trade-off of exploitation and exploration, the reward policy is a hybrid policy consisting of the random policy and the current policy. During policy training, we train SAC with both the offline dataset and the collected simulated data. Here, we adopt a weighted critic loss with the discriminator to downweight potentially harmful simulated data. The key insight of the weight is that for in-distribution states, since the offline dataset already includes them, we downweight these samples to avoid inconsistencies in Q-value estimation. For all these states, we require them to supplement the dataset, so there is no need to downweight them. We first evaluate our method on D4RL benchmark. Specifically, we test 12 datasets on 3 locomotion tasks. For the inaccurate simulator, we modify the original simulator with 3 different dynamics gaps. For baselines, we compared with offline RL, online RL, and hybrid offline and online RL methods. As we can see from the table, always outperforms the baselines in most of the tasks. In addition, we compare with SAC and H2O under different dynamics. The results are shown in Table 2. Always consistently outperforms H2O, demonstrating that Always can utilize the simulator better than H2O. Here are some qualitative results on 3 medium replay datasets. BC performs poorly on low-quality data. Offline RL methods can only find the suboptimal policy within the dataset, and SAC suffers from the dynamics gap and performs poorly. H2O cannot fully utilize the simulator and behaves poorly, while Oris, in contrast, can achieve good performance. Moreover, we tested whether Oris remains effective when the amount of data is reduced or when the simulator becomes more inaccurate. As shown here, the performance of most baselines drop dramatically as the amount of data decreases, while Oris only drops 8%. When the inaccuracy of the simulator grows, SAC and H2O performs poorly, while Oris rebounds to the inaccuracy and the score only drops 3%. Finally, we conducted an evaluation of Oris on a real-world manipulation task. The task is to pick and place a block. We first collect an offline dataset with the real-world Canova arm. After that, we interact with the simulator and train on both the offline dataset and the simulated data. Here are the experimental results. We can see that only Oris can complete the challenging task due to proper utilization of both the limited offline dataset and the inaccurate simulator, which shows the effectiveness of our methods in the real-world applications. These are our conclusions. We produced the initial state distribution and use a hybrid route policy to address the exploration-exploitation dilemma. Then we reweight the simulated data to deal with the dynamics gap. Extensive experimental results demonstrate the effectiveness of our method. Thanks for watching.